All right, guys, so I'm just going to run through and do these. This is the Chapter 3, Part 1 review. So the first part is 1 to 17, every other odd, starting with number 1. So this first section, we are computing the average rate of change. So it gives us a function down in Figure 1. And so what they want is the average rate of change from 0 to 2. So let me actually put that picture. So average rate of change, what you can think of that as is the slope of a secant line. So from 0 to 2, this is literally like Algebra 1 stuff. Like you pick points off the graph and then calculate the slope, which is also known as the average rate of change. So here's a coordinate point 0, 1, and then at 2, there's a coordinate point 2, 7. So literally what we're doing is taking those points. So you have a coordinate point at 0, 1, and then you have a coordinate point at 2, 7. Classic algebra stuff, change in y over change in x. So we've got 7 minus 1 over 2 minus 0. So 6 over 2 gives us an average rate of change of 3. And when I asked for the graphical interpretation, like I said, that's the slope of the secant line. So that's what we just found there, was the secant line from point to point and what its slope was. So the next every other odd would be 5. And for this one, we are doing the limit definition. Make sure you know how to do this because you will still need to do this on the test. So our function is x squared minus x, and I know this might be a little painful now that you know the easy way, but for the AP test it's still important to know how this definition works. So we had a 4-step process. Step 1 was to find f of a plus h. So here, let me write out what our actual, in case we forgot what this was. Okay, so like that. So we have a 4-step process. Step 1, step 2, step 3, and then step 4 was to take the limit. So first we want f of 1 plus h. So that means we're taking my function, plugging in a 1 plus h, and then kind of simplifying algebraically as much as we can. So this requires foiling, 1 plus h, 1 plus h. So that'll turn out like this, and then be careful. Make sure you're subtracting both of those pieces. So the 1's will cancel, which is good. And then 2h minus h, and then there's an h squared. Okay, so that's my step 2. That's step 1, and then step 2 I take what I left off with in step 2, because that's this piece right here, and then subtract f of a. So f of a is what I get when I plug 1 in here. So 1 squared is 1 minus 1, and that just ends up being 0. Remember what I've said at the end of this step, there shouldn't be anything that doesn't have an h in there. So that's nice. These cancel out, and I'm still just left with this. This is not typical. It's not typical that step 1 and step 2 have the same thing, so don't decide that that's like a shortcut. The only reason that happened here is because f of a was 0, so we weren't subtracting anything. Step 3, remember we take what we left off with in step 2, which is the numerator here, and then finish off the quotient by dividing by h. Reduce that down, I get a 1 plus h. So that represents the slope of the secant line between 1 and 1 plus h. So now, finally, I do step 4, and I take the limit as h approaches 0 of that expression. And so I wasn't able to take the limit up here because I would have a 0 in the denominator, but after all the simplifying, here I can just sub the 0 right in. And so I end up with 1. Okay, what they're asking for next is the tangent line, now that we have that. So this is an important reminder right here. Here's point slope form, which you guys are going to use for your tangent lines, and you can just leave it there. So y minus, in order to find the y value, you take what they give you and you plug it into the original function. So we plug that in. We know from one of our steps that we get 0. And then m is the slope at that point, so that's 1. And then x minus, and they always give you the x value. So this is just y. If we distribute that 1, which doesn't do anything, we get x minus 1. So that is our tangent line. All right, next every other odd jumps us to 9. Okay, so then we are again using the limit definition to compute something in there. So we've got y equals 4 minus x squared. This time the directions are asking us to find the actual derivative. So when we're finding the derivative and not just the derivative at a point, it'll slightly adjust this formula to use x's instead of a's. because a's were one specific x value. Here we're just generically going to use an x so that we end up with a function at the end instead of a number. So I have the same four-step process. I'm going to find f of x plus h. So plug that into this function, 4 minus x plus h quantity squared. So be careful with the subtraction. I'm going to write the foiling first in parentheses. And then you can carefully subtract. So we subtract every single one of those pieces, which means they're all going to end up negative. Careful with signs. They can throw your whole problem off. So step 2, we take this, so exactly what we left off with in step 1, and then subtract the original function f of x. So I'm going to subtract this quantity. And then remember what I set up above. At the end of this step, every single term that you have should have a factor of h in it. So 4 minus 4 will cancel, and then I have negative x squared minus negative x squared. So those will also cancel. And I just have 2 terms left, and they do both have a factor of h. So that means I'm good to move on to step 3. Step 3, I take what I left off with from step 2 and finish off the quotient. So negative 2xh minus h squared. Divide by h and reduce everything down. So I get a negative 2x minus h, and again, that represents the slope of my secant line. And finally, with step 4, I am going to take the limit as h approaches 0. Okay, and again, at this point, I can just plug the h right in. H is 0, and that leaves me with a negative 2x. So now that you guys know how to do these by hand, you should be able to kind of confirm that, yes, your answer should be a negative 2x by using the power rule. So you can write y prime, that's our derivative notation, equals negative 2x. So that's a derivative function rather than just the derivative at a specific point. Okay, next, every other odd would be 13. This is asking us to express the limit as a derivative. So let me write down exactly what we have here. And this is why it's super important to still know that limit definition, because the AP test loves asking this question. It'll give you something that just looks like this super weird quotient, but they actually want you to figure out what the function is, what you're trying to take the derivative of. So remember, it's supposed to be like, this is your generic form. I had this written up above. Okay, so f of a plus h, because what we really need to figure out is what function are they trying to get us to take the derivative of, and at what point. Okay, so f of a plus h, it's pretty clear that a is 1. So, because this a plus h is written as 1 plus h here. So the point they're trying to get us to find the derivative at would be a 1. And then 1 plus h was plugged into some function. What was that function? Well, it appears to be the square root of x. So if we take this function and plug that stuff into this formula, you can see that what we're going to come up with is this. So f of 1 plus h, if I plug a 1 plus h in here, I get this, minus f of a. If I plug a 1 into this function, I get 1, and then of course the h is just part of the formula. So they are asking us to find the derivative of this. I'm not entirely sure if they actually want us to find the derivative. I suppose we could using a power rule. So this is x to the 1/2, and that allows us to use the power rule. And so f prime, remember the 1/2 comes out front, and then our old power, you subtract 1 from it to get the new power. So that's the derivative that they're looking for. The derivative at 1, I could just plug that right in. And of course, 1 to any power is still 1, so then times 1/2 would leave me with 1/2. So what that means is if I were to take this and simplify it down algebraically, which would require a lot of work, I would end up with 1/2. Okay, next we move on to 17. Okay, and 17 is asking us to find f of 4 and f prime of 4. It gives us an equation, and then we are finding the tangent line. So the equation is y equals 3x minus 14. And it asks us to find f of 4 and f prime of 4. So it gives us x equals 4. We find f of 4 by just plugging into the original function, so just right in here. Okay, so the y value, when x is 4, the y value is negative 2. And then it asks us to find f prime of 4. You can't find f prime at a value until you find f prime in general, if you're doing the quick derivative rules anyway. So the derivative of this Derivative of 3x, since it's just a linear piece, is just 3, minus, and then the derivative of 14, since it's a constant, would be 0. So my derivative is 3. We probably could have told ourselves that if we looked from the very beginning, because this is linear, and so derivative is the same as slope on just a linear function. So if f prime of x is always 3, that means f prime of 4 would be 3, since it's a constant derivative throughout its entire domain. So that's what I have so far. They're asking to find a tangent line, so we can plug into our point slope form right here. So y minus, the y value we found was -2, so this becomes +2, equals the slope, and then x minus the x value. Now, you can just leave it like this. I'm just going to go a step further just to show you something. So if I distribute this and then subtract this 2 from both sides, notice what I come up with is the exact equation that I started with from the beginning. So that's kind of a new little fact that you can add to your toolbox there. If you have just a linear equation, the tangent line to any point is just that exact same linear equation. Tangent lines are linear, so if the function itself starts off linear, it's not going to be any different of a function. Okay, 18 and 19, I can pretty much just show you guys the graph for. So we've got all these pictures. It says each graph shows a function and its derivative. Determine which is the function and which is the derivative. So just to tell you guys right here, remember our kind of like, cubic has a quadratic derivative. Quadratic has a linear derivative. Linear has a constant derivative, and constant functions have 0 as a derivative. So if you're looking at these two, I've got one quadratic piece, one linear piece. That means the quadratic is the original function, and then the linear piece is the derivative. Just to prove it to you, though, notice how this function is increasing, then stops, and then decreasing. If we look at its derivative is positive, and then 0, and then negative. Increasing has a positive derivative, decreasing has a negative derivative, and if the function stops, then the derivative would be 0. And this is what I mean by stopping, having like a min or a max, a slope of 0. So A is f, B is f prime for this one. This one's a little bit different. It appears we've got two trig functions right here. So B looks like just a run-of-the-mill sine function, and A looks like a run-of-the-mill cosine function. So we know that the derivative of sine is cosine, and so if we say this is the original, that's sine, B, and then A is cosine, so that's the derivative. So here B is f, A is f prime. Let me just show you a couple features we should be looking out for. Notice that this max, the derivative has a point of 0 here, and this min, the derivative has a point of 0 here. Now, you might be saying like, oh, well, these are the same. Like here, A has min, max, min, and this function has zeros, but the increasing, decreasing behavior is actually opposite of what you need. So again, B is the original derivative. Notice it decreases, increases, decreases. As it's decreasing, A is negative. As it's increasing, A is positive, and as it's decreasing, A is negative again. If we kind of flipped them, let's say we thought this was the original function, A is increasing, its derivative should be positive, but this is negative. So that means B is not the derivative of A, it means A is the derivative of B. Okay, and then this one should be fairly straightforward using our rules with the exponents. B is clearly a cubic function, and A is clearly quadratic, so that means B is the original and A is the derivative. But again, some features to look out for. See how this has a local max right here, and this is on the x-axis. Then we've got a min right here, and this is right on the x-axis. And B goes from increasing to decreasing to increasing, and A is positive, negative, positive. All right, 19. Which one is the derivative? Okay. So again, the first thing you want to look for is the mins and maxes. So we've got a max somewhere in between -2 and -1. So the derivative should have a 0. So that one does, still in the running. That one does not, so B is out. And that one does. Okay, so it's either A or C. We've got a min between -1 and 0. So the derivative should have another x-intercept there. This one does, but it doesn't look like it's quite where we want it to be. This one's right in the middle, so C is looking pretty good, but let's look for like at least one more piece of evidence. This one has another max between 0 and 1, so I should have another 0 on my derivative. And this one does not. This one has a 0 at a, but this doesn't have a min or max. Or I'm sorry, this one has a 0